Okay, next up we have Zihao Li, who's going to be talking to us about insights into cosmic evolution of gas phase metallicity gradients from James Webb. Crystal, I'll ask you a question while we're waiting. I'll put you back on the spot. For the Lyman alpha emitters, right? The question was whether or not these mergers were driving the Lyman alpha emission. But I guess what I want to figure out is we looked at this with Callum Witten, where we found something quite similar. And there's no control sample. So do you know if the merger is inducing the Lyman alpha emission, or you're in a protocluster environment which drives the merger but also simultaneously creates a bubble, and that's why you see the Lyman alpha? It works. Okay. So Richard, I'm sure you have a lot of insightful comments, but we're going to put Crystal on the spot for half an hour, starting at 5:10. So we're going to move on to our next speaker, who's going to talk to us about gas phase metallicity. Thank you.
Okay. Hello everyone. I'm very sorry for the inconvenience. And I'm Zihao Li from Tsinghua University, and I'm moving to Cosmic Dawn Center as a PhD student this week. And my topic today is about gas phase metallicity gradients from James Webb. Here I give a very brief introduction of bathtub model of galaxy chemical evolution that the galaxy live in a complex environment, and they are gas inflows into the galaxy, and the star formation turn to the twisting gas into metal enriched gas through outflows. And in such a baryon cycle, the galaxies are growing, and the gas phase metallicity and its distribution in the interstellar medium is a key proof of such processes in the baryon cycle, and also say Shannon talked more about this. And the metal distribution in the galaxies prove this chemical evolution, and in many numerical simulations we see that the metal distribution is not uniform. Instead, we see the profile of metallicity, and in these fire simulations, we can find that the metallicity, the gradient of metallicity is active. That is, it's metal rich in the center and metal poor in the outskirts. And in the TNG15 simulation, we see similar. Sorry. Oh, yes, yes. Thank you, thank you. Okay. So, in the simulations, we see that the distribution of the metal in the galaxies have a variety of kinds. And so, how about observation? And here in our previous work, we use HST to probe the metals in galaxies. For example, in this work, we probe galaxy evolution in protoclusters at cosmic noon. We use HST slit spectroscopy, and in this protocluster, we take the slit spectroscopy for the member galaxies, and we find that the member galaxies inside the protoclusters are more metal poor than the coeval galaxies in the blank field. So that we think the metal dilution in the photoclusters is stronger, and moreover, we study the spatial distribution of the metals in the galaxies through a spatial resolved spectroscopy, HST gradient, and we can find the many emission lines that are spatially resolved, and we use the O3, O2, H beta, and H gamma to compare the metallicity at different regions of the galaxy. And interestingly, we find that in this galaxy is metal poor in the center and is metal rich in the outskirts. And if we plot our observation and compare to other literature work, we find that these member galaxies have positive metallicity gradients. That's a pretty different. So we think the high fraction of this positive gradient indicates that the pristine gas are penetrating into the galaxies to dilute the metallicity in the center, so that we can find the inverted metallicity gradient. So how about in the JWST era? Here are some of my very preliminary results. So be cautious to the new results from James Webb. And in our galaxy sample, we collect many galaxies into 3 James Webb surveys, including NGD, Classifier, and Frisco. These are all wide field slit spectroscopy surveys. So all of the spectra we get are spatially resolved so that we can map the distribution of every O3 emitting galaxies in our sample, and here we build a sample that across the largest redshift and measure the distribution inside the galaxy. So for the galaxies in the NGDIF sample, here I show an example of the James Webb near-ray spectra. You can see that the oxygen 2, H gamma, H beta, O3, and H alpha are both spatially resolved. So we can use the spatially resolved map of emission lines to infer the spatial distribution of galaxies, of metals in this galaxy. And here is the map of the metal distribution of this galaxy, and we find similar trends that it's metal poor in the center and metal rich in the outskirts. So it has inverted or positive metallicity gradients. And similarly, for the very high redshift galaxies, and this is an example in the physical survey that we can find the H beta and oxygen 3 are spatially resolved. So we can then use the O3 and H beta to derive the metal distributions in this galaxy. And we can find that this galaxy has a nearly flat or negative gradient of metallicity. However, for individual galaxies, the H beta are rarely detected in James Webb near comparison spectra because of the no similar to noise. So to enhance the similar to noise ratio, we stack our galaxy sample to build a stacked image and measure the average profile of O3 and H beta, and then get the profile of metallicity. So in the sample of Aspire, all of the sample galaxies are in the F356W filter, and we can find the stacked map of O3 and H beta, and we measure the normalized brightness profile, and then we use empirical calibration to get the profile of metallicity. And similarly, in the physical survey, the galaxies are in the O3 emission lines are in the F4W filter, and we get the profile for those galaxies at redshift 7 to 9. And we find that the profile of metallicity are very negative. So this is the first time we measure the metallicity at this high redshift. And so here we plot the evolution of metallicity gradient with redshift. And here the red points are our measured results, and the gray are the results in the literature. You can see that we really explored a new redshift geometry space, and we found a very interesting trend of the evolution of metallicity gradients. That they peak at redshift 2 and they decline as the redshift go higher. So we want to know what makes the gradient of metallicity flat at redshift 2. So we find some unlikely explanations that probably a feedback at redshift 2 is strong, or the gas accretion at redshift 2 is stronger, so that they can dilute the metal in the galaxy that flat the gradient. And also in the fire simulation, they find similar trends for the member galaxies that at redshift around 2, the specific star formation rate is very high, and then follows the invert of gradients. So that the star formation and feedback plays a very important role in shape the gradients of galaxy. And as the redshift go lower, the star formation activity declines, and we can say that the gradients of the metal also declines. So we see such a trend of the metallicity gradient. And this is a smooth support that we can more clearly say that the trend of metallicity gradients in fire simulations. But as for gases at a higher redshift, why the gradient is so negative? And we compared our observations with many numerical simulations, and we find the feedback-free starburst scenario can well reproduce our observation. And yeah, just say Zhao Zhou or Avisha's talk about more details in the FFB. Not going to go into too much detail about this. But so then we compare our observation with FFB scenario. We want to know not only the spatial resolved metallicity, we want to know the stellar mass and star formation rate and the gas fraction inside of galaxies. So through our stacked map, we can measure the stellar mass surface density, and we measure the H beta surface brightness. We convert H beta luminosity to star formation rate density, and using using inverted case law, we measure the gas surface density and measure the gas fraction, and we compare our observations to the prediction from FFB. And here is our preliminary results with the comparison to FFB model, that for galaxies at redshift 2, the metallicity are higher than our galaxies. But for our member galaxies, even if the gas fraction is very low, the metallicity is still lower than the galaxies at cosmic noon. So in the FFB model, they predict that the star formation efficiency is very high, so that it can consume much of the gas, so that the gas fraction can be very low, but keep the metallicity still low. And also, our measured profile of the metallicity agree very well with the prediction of FFB galaxies, that they have a very negative gradient of metals. So here's our conclusions that we, for the first time, measure the cosmic evolution of metallicity gradients out to the 8. And we find the galaxy evolution pattern seems different at different cosmic epochs. That at cosmic dawn, the galaxies may follow the FFB scenario, and at cosmic noon, the spatial outflow or inflow can lead to diverse metallicity gradients. They are fluctuating around 0. And at present, the feedback and gas fission are weak to the galaxy for particular evolution. Here's our conclusion. Thank you very much, and I'm happy to take your questions.
Start with Richard.
It's quite nice, but it seems like you've done this all as a function of radius. Have you looked at how things vary, and if you would look at spatial variations? I'm just wondering if, as you go from high redshift to low redshift, basically things become more smooth or less clumpy, and I'm just wondering if the same result would hold if you would look at, like, clump to clump variations or region to region variations. I don't know how you do the analysis, but have you looked at the extent to which, if a high redshift object is really messy, that some of the radial variation might be smoothed out?
Yeah, the radial variations are smoothed out. So I'm measure the.
I'm just wondering if you might not have like a disk galaxy, but you might have like merger-like objects, and if you have merger-like objects and you have different regions, then you might not nicely segregate as a function of radius. And so I wondered if you looked into this issue at all.
Yes, it's a problem, but in our current analysis, we just smooth everything. So maybe we can use IFU to probe specific mergers to investigate if the metallicity patterns are different or not. So yes, I know. So it's a very complex topic. It's because inside the galaxy, it's very it has many different structures, but limited by the resolution or signal noise given the current data. So it's not necessarily not possible for now to say that. Yeah, it's
Great talk. Sorry, I think I missed. You must have mentioned this at the beginning. How are you measuring the gas phase metallicity, and which emission lines do you have available to do this measurement?
Emission lines for the for the galaxy at this redshift, we have the 5 emission lines. Many we use O3, O2, H beta to measure the metallicity, and use H beta, H alpha to measure the pharmacy equipment and the correct product. However, for the heavy H gases, we can only get access to O3 and H beta simultaneously. So we only use the two lines to measure metallicity. Maybe higher.
Okay, I think that's a good place to stop for coffee. So let's thank all of our speakers again from this session.